we could do is just call it an 8 which has been turned down infinity. But this is not practical. So instead we call it aleph null. And aleph is the first letter in the Hebrew alphabet. So this is what I call this particular kind of aleph. And then we just write down one more. And then it says if you take a letter out, take a real number. This we call C. And this is for the continuum. So here you see 0, N, aleph naught, and C. These are some characters. I will come back to those in just a minute, but let me first mention the fact. And this is almost a tautology, particularly if you think about this for a girl analogy. It says that suppose that X and Y are finite sets. And I'm going to be rather informal about it. By finite sets, I just mean they have finite elements. And as you know, there is actually a very beautiful way of characterizing finite sets in terms of a finite set is a set with a property that every injective map from X to X is surjective. This is how you can define being finite. So hence, an infinite set is a set for which there exists an injective map which is not surjective. But here I'm just really thinking about it as finite elements. If this is the case, then the cardinality of X is equal to the cardinality of Y if and only if X and Y have equally many elements at the same number of elements. And this is really something that in principle requires a proof. But what it really says is the following. Suppose you have two sets with, say, 28 elements. The first set is 1, 2, up to 28, and the other one is the number of letters in the alphabet. I think that's 28, maybe 29. Maybe 28 letters in the alphabet. Then these have the same cardinality, so that means that you should be able to find a bijection from the set of numbers 1 up to 28 to the letters. And it's very easy to do. 1 goes to A, 2 goes to B, 3 goes to C, and so forth. And there are actually 28 factorial possible mappings. This is not the only one. There's a huge number of mappings. But it's very intuitively clear that this is a true thing. So I'm just mentioning this. And hence, as a consequence, the cardinality of a finite set is equal to n is equal to the number of elements in X. And this, of course, only works for finite sets, because for infinite sets, how many elements are there in natural numbers? We already discussed that infinitely many, but there are also infinitely many real numbers, and it turns out that there are more real numbers than there are natural numbers. So we have to distinguish it in some more refined way, and this is what we do by putting in these things here. Then now, while it is not cardinal numbers, in increasing order. So the smallest cardinal number is 0, the cardinality of the empty set, then comes 1, 2, a 2-point set, 3-point set up to n, and then comes aleph naught. And aleph naught is the smallest infinite cardinal. This is also something you can actually prove. There's a little bit more content to this statement, but I will not prove it. I will just tell you this is how it is. That there's no infinite set whose cardinality is strictly smaller than the cardinality of the numbers. And then comes C, whatever it, and so forth. Then we, at this point, mention C was a cardinality of the numbers. Then we mention some facts at this point. So I mentioned already this is the smallest infinite cardinal, and we're really most interested in these cardinals here, although also a little bit one fact, these two numbers are different. This is bigger than this. There are more real numbers than there are natural numbers. The next thing is this list continues infinitely in the range. Whenever we have a set, there's another set bigger than the previous set. And actually this would be one of the theorems you will do in classes, I think this week. Every week there will be a weekly theorem for you to do in exercise classes. And the result saying that this never stops is a result you're going to prove, namely, whenever you have a set, then the cardinality of that set is strictly smaller than the cardinality of the set of the powers of that, the set of all subsets of that set. So what I'm saying here is a cardinality of X is always strictly smaller than the cardinality of P of X. And hence that list can never stop. The next thing is there any thing between these two? There is a cardinal number strictly between these two. This really says the following. Suppose you have a subset of the real numbers. Is it then true that this subset either has the same size as all the real numbers, same cardinality as all the real numbers, or it has the same cardinality as the natural numbers, or it is finite? Is that true for every subset of the real line? So either same cardinality as all the real numbers, same cardinality as the natural numbers, or finite. So this should be a very straightforward question. And the answer is, we don't know. And not only don't we know, we can prove we don't know. So there's a set of actions for set theory sample function that's defined a consistent set of actions for set theory. And this particular question, which is called the continuum hypothesis, is independent of these actions. So you can choose to take the continuum action, because continuum hypothesis, the continuum hypothesis, you can include it in set theory, and if you include it, then there are no sets in between. And it's consistent, or you can throw it away, and then there are sets in between. Both are correct mathematics. And this is somehow really amazing. Then we say that normally we adapt the continuum hypothesis. So normally we adapt the convention that there are no cardinals between these two. But you can completely choose. So this is really, and also I think this particular thing tells you, I was talking last hour about arbitrary subset of the real line and can we measure them. And this tells you how little we know about an So that means that the cardinality is here. That means, hence, let us look at here, fact x is countable if and only if one of the following holds. So there are three possibilities. One is that x is empty, and that corresponds to its cardinality 0. Another is that x is finite. Then x can be written x1, x2, up to xn, and the cardinality of x is the number of elements that will be this number n. So finite sets can all be written this form. And the third possibility is that so the first two cases correspond to either here or we are somewhere here, and the last possibility is right here. Cardinality of x is equal to 100 is equal to the cardinality of the numbers. And then in this case, this is why it is called being countable. We can write x in this form here. x1, x2, x3, x4, we can enumerate the elements in x. So every set x that has the same cardinality as that number could be written here. And to see the data, this is not difficult to see. Take f that goes from the natural number to x, a partition. Then we can simply say that we can put xn to the f of n. And then we have that x is the same thing as f of n, because f is effective. And this is the same as x1, x2, x3, and so forth. And no elements are repeated in this list because it is injective. And this again is then by definition of it. Simple to find x1, x2, x3, and so on. So this proves this thing here. So countable sets have the quality that you can write down the elements in list form, either infinite or finite. And okay, so then we can just use one second to give the easiest example, and then I will give them the remaining examples tomorrow. Put it here. We are going to see many examples of sets which are countable and also some which are not. Maybe the easiest example is an example 2 in the book. Let E be the set of even numbers and O be the set of odd numbers. And these are subsets of the natural numbers. Then it is true that the cardinality of E and the cardinality of O is equal to the cardinality of N with alpha. They are countable. And even you have seen, we have